Good morning, guys.
Morning.
Good morning. Okie dokie. So, how was your weekend? Wet? Okay, guys. Any questions yet? No. So let's just see if we can. Catch up on what we already have done. We could say it's okay if this here was one cycle. We should also say it's okay it will be the same as one wave. Oops. Now when we measure from here to here, in terms of time, that was what we called period. Yeah, okay. And we are going to have, okay, use a unit of time to express that. We also said that if, for instance, in 1 second, let's say it's okay, the number of cycles that we had per a second was going to be referred to as the frequency. Okay. Now it could be expressed as, okay, as the number of cycles per second. Or more correctly, was going to, yes, okay, be expressed in what we call hertz. Okay. Now another thing that we now also know is that period was going to be, yes, okay, inversely proportional to the frequency. Not just that, but we also said that, okay, yes, period and frequency were reciprocal. Did you guys get that? Right, okay. Well, it means says, okay, it's going to be, okay, the unit if we find this, okay, said millisecond, then the frequency was going to be kilohertz. If we said, for instance, microseconds, that was going to be megahertz. Okay, mainly because, as we said in chapter 1, milli and kilo are reciprocal units. So is micro and mega. And if you want to go SOK even further, you can see SOK if you see nanoseconds. That is going to be SOK. Gigahertz. Yep. So for instance, if our frequency was, let's say, 10 megahertz, then your period was going to be SOK. 1/10 of a microsecond. Clear? Okay. If your frequency, for instance, okay, was 2 kilohertz, then the period was going to be half a millisecond. Is that clear? Did anybody get any of all this?
Yeah.
Okay. Now, guys, when we talk period and frequency, we have already established, please, the period is inversely proportional to frequency, but we also says, okay, but what we mean is, okay, standby being inversely proportional is that, okay, a period increases, the frequency will decrease, or a period decreases, the frequency will increase. But besides being as okay, just inversely proportional, both period and frequency are also going to be reciprocal, which may mean that their product will be equal to 1. Now, guys, and as we said, for instance, okay, let's use this command. Because if we had a cycle, and it's okay, we measure the time of one cycle in terms of time, that was what we called a period. Now, guys, as I said the other day when finishing, we is okay, we're going to take a little jump. Or at least for now, it's okay. Skip or 3 bigness parameters, and that mainly what means that okay, today we'll start on page number 33. Okay, guys. So you can all just okay again on to page number 33 in your books, and what you will see is that we talk about wavelength. Now, guys, if you just break this term here up, you can mainly say, okay, it's going to be made up of 2 things. One is going to be wave. And we can say, okay, this is our wave. Okay, because we already know that, okay, yes, one cycle can also be as, okay, referred to as, okay, as one wave. Is that clear? Okay, the next thing is going to be as, okay, what will be length? Which is this. Which you mainly will see as, okay, the same as period, but here it's okay, we're not talking about the time, but rather about as, okay, the length, which is going to as, okay, be measured in the unit of distance. Did you guys get that?
Yes.
Yep.
Yeah.
Right, okay. Okay, so what's going to be the wavelength? We can mainly say, okay, it's going to be the distance. Or if you English, just, okay, take the word length of one complete cycle. Yeah, okay. Now you can say, as, okay, probably as, okay, the reason that, okay, as the word distance, maybe more preferably we call it as, okay, length can also be taken in terms of time, right? Okay. Okay, you watch a movie which is very, very long. You say, okay, that was a long movie. Okay. Okay. Although, yes, okay, that will be as, okay, a length in terms of time. But when we say distance, well, okay, yes, there is probably as, okay, no doubt about what kind of length we are talking about. Clear? Okay. So the time for one cycle to complete, that was what we call period. The length of the one cycle is going to be as, okay, what you will call the length. Okay, guys? And please, 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 it's going to be as, okay, a straight line like this. That will be the length. Yeah, okay? Whereas, okay, as for instance, okay, if you had gone like this, that would mean that's okay, be as, okay, bigger or smaller, all dependent upon as, okay, the amplitude. So you can have waves with same wavelengths, but different amplitudes. And likewise, yes, okay, waves with same amplitudes, but different wavelengths. Clear? Okay, but this distance from here to here, that is going to be the wavelength. Okay, did you guys get that? Okay.
Yeah.
Okay, and saying yes, okay, it means yes, okay, going to be measuring the distance. That's why it's okay. We mean yes, okay, just use a unit of distance, or which we as okay, still can is okay call length. Okay, which can be as okay any fraction or multiple of a meter. Did you guys get that?
Yes.
Good. Okay. So it's going to be as okay any fraction or multiple of meter. But as okay, in ultrasound we only as okay are going to as okay see fractions of a meter. So something like, for instance, okay, centimeters and or millimeters. Okay. Now, guys, as far as, okay, the typical range here, well, okay, it is written in the book, but it's really not something that you need to remember. Okay, so this is one of those typical values that you don't need to memorize. No, sorry. Yeah, you may need to. Sorry. Well, what is it? It's 1.01 millimeter to 0.8 millimeters. Is that clear? Now, please, guys, this 0.1 millimeter can also be written as 0.1 multiplied by 10 raised to the power 3 meters. Whereas this 0.8 here can also be, sorry, multiplied by 10 raised to the power minus 3 meters. Yeah, okay. You could also go and say, it's okay, 0.1. Oh, let's go this way. 0.0001 meter or 0.00 meters. Or if you want to, yes, okay. You can write 10 raised to the power minus 4 meters or 8 raised to the power minus 4 meters. Did you guys get that? So the smallest wavelength is anything, it's like, it's okay, 1/10 of a millimeter. The greatest is, okay, yes, 0.8 of a, or that's okay, 1/10 of a millimeter. Clear? Okay. So that's just okay. It's typical value. Now, guys, one thing, and that's what's going to be as okay unique when we talk about the wavelength, because this fellow here is okay. Is going to be determined by both your source. Now, what was your source?
The transducer.
The transducer. Yeah, okay. And your medium, which is going to be the tissues. Did you guys get that? So out of your 7 parameters, okay, the wavelength is the only parameter that is determined by both source and medium. Okay, the source is going to be as okay your transducer, whereas medium is going to be the tissues. Did you guys get that?
Yep.
Okay. Now we can mainly say, okay, a Y source. Y source or transducer. Mainly because, okay, it's going to determine the wavelength, mainly because that's what also is, okay, determines the period, which will end up, yes, okay, determining the wavelength. Okay. Or how, yes, okay, the source or your transducer actually is, okay, sets the wavelength of your sound wave is something that we'll talk more in detail about in a later chapter as well. But for now, just remember this much that, okay, as the wavelength is going to just, okay, be determined by the source. Yeah, okay. The whole talk about, yes, okay, the tissue or the medium, we will get to that in just a little bit. Okay, when we talk further details about, yes, okay, our wavelength. Is that clear? Okay. Now, guys, whereas is this fellow here is okay adjustable? No, just because it's okay, just like your period was not adjustable. Likewise, is the wavelength also going to be non-adjustable unless you change to other transducer. Okay, unless it's okay, you change the transducer, which may it's okay have a bigger or shorter period, which will give you is okay. Well, you can say it's okay, a different source, right? Okay, which will give you is okay a greater or shorter wavelength. Okay. Did you guys get that?
Yep.
Good. So, what is one of our, yes, okay, important relationships that we now need to establish? Now, let's just say that, okay, yes, this here was one cycle. Yeah, okay. Now, what we said was that, okay, yes, if you measure the time from the beginning of the cycle to the end of the cycle in terms of time, that was what we call period. Clear? Okay. The same thing. Let's choose, okay, so let's brighter color. The same thing by us, okay, we measure that in terms of, let's say, length. That was what we call wavelength. Clear? Okay. Now let's just, okay, let's take another wave. Wave again, yes, okay, we'll say it's okay, this here, oh, sorry. If we measure this in time, that'll be, yes, okay, the period of this wave here. Where, okay, we measure the same thing as, okay, in distance or length. That'll be the wavelength of this wave here. So yes, okay, when comparing these two waves, we can just say, yes, okay, A and B. What do we see that wave A has? Comparing the two. It has a shorter period. Where you also can see it's okay that it has a shorter wavelength compared to B, which it has a greater period, which also gave it a greater wavelength. Did you guys get that?
Yes.
Okay. So what does that tell us? That period is directly proportional to wavelength. Right. Okay, because we may say here that yes, just for instance, that the time that it took one cycle to complete, let's say was, that just says 1/10 of a millisecond. And not to go too much in confusion, because the wavelength could have been 1/10 of a millimeter, for instance. Whereas we over here says here the period was, that says 1 millisecond. And let's just assume that yes, the wavelength had been 1 millimeter. Did you guys get that?
Yep.
Good. So this was just relationship number one. That period is directly proportional to wavelength, where we can mainly say greater period, greater wavelength. Okay. Shorter wavelength, that's due to a shorter period or vice versa. Now, guys, what else have we also established? Is that this period here also was inversely proportional to what we call frequency. Right? Okay. Which mainly would mean that, yes, if we had a greater period, we will have a lower frequency. If we had a shorter period, we will have a greater frequency. So since period and frequency are inversely proportional to one another, and period and wavelength are directly proportional to one another, that causes that, yes, this wavelength here is also going to be, yes, okay, inversely proportional to wavelength or frequency, sorry.
Mike?
Yeah.
So, if something is inversely related, are they always reciprocals?
No,
No? Would wavelength and frequency be reciprocals though?
no,
Okay.
they're just inversely proportional.
Okay, thank you.
Okay, so the reciprocal is okay as far as we are concerned, is only as okay going to as okay apply to periods and frequencies.
Oh, so just period and frequency. Okay,
Exactly.
thank you.
Okay. Okay. Wavelength and frequency will be inversely proportional, which mean that okay, yes, when we have yes, okay, where can we say okay? If you for instance, okay, have a lower wavelength, we will have a greater frequency. And vice versa, okay, it's okay, when we have a greater wavelength, we will have a lower frequency. Okay, so the reciprocal thing is only between period and frequency. Okay, or when we talk about okay, something measured in times versus how many times is it that occur in a specific period of time. That's going to be reciprocal. Did that make sense?
Yes,
Okay.
thank you.
So the relationship between wavelength and frequency is not reciprocal. First of all, it's okay, length is not related to, as okay, or we can say that the physical length of a something is not going to be as okay related to as okay how frequently a thing will occur. Okay, but mainly because okay, the greater the time, that's okay, the greater the time it takes for the wave to complete. That's okay, the greater is it that its length will be. Okay. So pretty much okay, yes, it's just a well, okay, you can say it's okay, it's a matter of yes, okay, copy and pasting is okay, an older relationship. Okay. So just because period and frequency are directly proportional to one another, they both will be reciprocal to the, inversely proportional to the frequency, but it's only going to be the period that will be reciprocal. Did that make sense? Okay. Here I just says okay for the matter of okay simplicity say okay as if okay as our period was 1/10 of a millisecond, then the wavelength is going to it's okay be, or we could just assume that the wavelength was 1/10 of a millimeter. Okay, where I say okay, well we increase the period, let's say okay 1 millisecond, well okay the wavelength is going to be 1 millimeter. Okay. Okay. Did that make sense? But actually, as okay, what we can say here is okay, as in this case, yes, okay, what's going to be our frequency if our period was 1/10 of a millisecond? The frequency would have been 10 kilohertz. In this case, it's okay, where our period was 1 millisecond, then it's okay, the frequency was going to be 1 kilohertz. Did you guys get that? But for now, it's okay, just remember this much at least, okay, until like we get further on ahead with the wavelength, that period and wavelength are directly proportional. What we already have learned is that period was inversely proportional to frequency. We also make as okay, wavelength inversely proportional to frequency because wavelength is directly proportional to period. So if we put all of this here as okay in one straight line, we can say it's okay. We have period, we have wavelength, and we have frequency. Where we mainly can say that, okay, yes, if the period increases, the wavelength increases, and the frequency decreases. And or if we went the other way around, we said, if the period decreases, the wavelength decreases, and the frequency increases. That mainly established that, okay, yes, period and frequency, period and wavelength are directly proportional to one another, but they are both inversely proportional to frequency. Or we can do it this way and say it's okay, we have let's say it's okay that its time span from here to here is okay, it was 1 second. Likewise here. We can say, okay, this is the time span of 1 second. Okay. Here we can say, okay, 1, 2, 3, 4 waves. Okay, so in 4 seconds, so in 1 second, we got, yes, okay, a total of, we can say, okay, 4 waves. So that's going to be, yes, okay, because that's okay, a frequency of 4 hertz. What we can talk about the period is that, okay, the period for sure is going to be, as okay, 1/4 of a second. Yeah, because 1/4 plus 1/4 plus 1/4 plus 1/4, or 1/4 times 4 will equal 1 second. Right? Okay. Did that make sense? Clear? Okay. But we can mainly says, okay, that will be the period for each cycle. But when you measure it's okay, from let's say from here to here in terms of time, that would be the period. Whereas, okay, we take a same wave and measure from here to here, yes, okay, in terms of distance or length, that will be, yes, okay, its wavelength. Okay. Just to say, okay, you can say, okay, 0.2 millimeters, for instance. Did that make sense?
Yes.
Okay. Now, if we just go and say, it's okay, in the next example here, it's okay, what do we have? Oh, shit. Right, okay. Where we can say, it's okay, this is mean as okay, going to be as okay. Now, how many waves do we have in 1 second? That's going to be the frequency. We have 1, we have 2. So that's our frequency, 2 hertz. Okay, where okay, as when we measure from here to here in terms of time, that's going to be the period, which is going to be okay, half of a second. Yeah, okay. There's okay, if you find this okay, measure from here to here in terms of distance, that's going to be the wavelength, which is going to be okay, 0.4 millimeters, for instance. So what did we see? Here did we have a lower frequency because the wavelength increased and the period increased. Whereas over here, it's okay, we have the opposite. Here we have okay, as a greater frequency because of a shorter period, which has okay, as a lower wavelength. Did you guys get that?
Yep.
Okay. If not, just okay, just copy and paste, just okay, the old relationship together with okay, as what we already have established from as okay, with the relationship between period and wavelength. Yeah, okay, this is me going to mean that may just mean that okay, yes. Due to this relationship here, that's how yes, okay. This relationship is also established. And since it's okay, this relationship and this relationship is established with this and this, that causes that okay, yes. How these two are related. But you can even check it separately and says, okay, period and wavelength are directly proportional. Period and frequency are inversely proportional. So that mainly call that okay, as wavelength and frequency are also going to be inversely proportional. But just as I showed you guys here. Here, okay. You can say it's okay. The shorter the period, well, okay, the shorter the wavelength, the higher the frequency. Yeah, okay. Greater period, greater wavelength, lower frequency. Okay. So an easy way of, okay, as you can say, it's okay, writing down your relationships is arrows up and arrows down. Okay. You can even color themselves, okay. Same color arrows, that's okay. That's going to be, it's okay, the relationships. Okay. But please keep in mind that, okay, as in this case, as okay, the reciprocal only applies to period and frequency. Did you guys get that? Okay. Any questions about this relation or these relationships here now? Nope. Okay. So what have you established? Greater period, greater wavelength, shorter period, shorter wavelength. Okay. Greater wavelength, lower frequency, shorter wavelength, higher frequency. Okay. Now, as far as, okay, the relationship between period and frequency was concerned, they were reciprocal. That would mean that, okay, as you multiply the two of those, the result equals 1. Clear? Okay. That does not apply to the relationship between wavelength and frequency. They are only inversely proportional, which means, yes, okay, one goes up, the other one goes down. Did you guys get that? Now, guys, that was the simpler part of wavelength. Oops, somebody already almost got choked on their sip of coffee. Okay, guys. Now, you guys remember your ANP? When we talked about tissues? Okay, you guys can get your Kleenex tissues out. Because that's okay. The tears may start rolling. Hopefully not. Okay, guys. Because in ANP, we said, okay, what kind of tissues did we have? We had epithelial, we had connective, we had nervous, and we had muscular, right? Okay. Now in ultrasound, you're going to just, okay, get introduced, just, okay, new kind of tissue. Okay. And that's me, that's okay, that's going to be, okay, in context to ultrasound. If you ask me specifically, it's okay, what tissues make up this tissue, I will say, no comments. So we call it soft tissue. Okay. So as okay. In this chapter here, and most likely as okay, in chapter number 6, you will hear the word soft tissue again. Now, the reason that we use soft tissue to discuss or talk about ultrasound physics because it's going to be as okay an intermediate tissue. It's not hard as bones and things like that, and it's not as okay thin or as okay less dense as gases. Okay, but is it going to be blood? No. Is it muscles? No. It's just okay as an intermediate kind of theoretically developed tissue. Clear? Okay. Because our question is still going to be as okay, what will be our wavelength? Because as I said earlier, wavelength was determined by two things. Source, which was your transducer, right? Clear? Okay. And the other one was what we called medium, which is your tissues. Clear? Okay. And what you will see is that, okay, yes, the intermediate tissue in terms of, yes, okay, that we talk about an ultrasound is going to be, yes, okay, what we refer to as soft tissue. Did you guys get that? Now, guys, in your book, everybody have their books? Okay, I know you have your books because you picked them up, but have your books open? Okay, guys, on page number 34. Everybody have their books open on page 34. If you see the last paragraph, or let's say it's okay, last two paragraphs. Now, one is written in bold letter, which says, okay, what is the wavelength of a 1 megahertz sound in soft tissue? And the answer is written down. It is going to be, okay, 1.54 millimeters. Did you guys get that? Did you guys get that? So,
Yes.
in soft tissues, now here's going to be, okay, a couple of factors. Okay, let's put it this way, guys. So what did we say? Let's do this way. So in soft tissues, we can say it's okay, frequency, and we can see it's okay, wavelength. Now, if the frequency is okay is 1 megahertz. Now you can actually, as okay, indirectly say that that's because, okay, the period is 1 microsecond. Yeah, okay. And okay, if we say it's okay, soft tissue, then the wavelength is going to be 1.54 millimeters. Now the question comes as, okay, how did they get this 1.54 millimeters? Now, guys, that's actually just okay, going to just okay be derived from what we'll call the speed of sound in soft tissues. Okay, which is going to be as okay as somehow intermediate. Or actually, that's okay, going to, that's okay, be 1.54 millimeters per microseconds. Now, guys, if your friends, that's okay, went to a tissue, let's say it's okay, a speed that was a greater speed than, okay, yes, than that of soft tissue. Let's, for instance, okay, say bone. Now, due to, yes, okay, a greater speed in bone, for instance, okay, we can say, okay, the speed would have been approximately as, okay, let's say it's okay, 3,000 millimeters per microsecond. But due to that, yes, okay, even if you had a one frequency transducer or one megahertz frequency transducer, we are going to have, okay, as a greater wavelength.
Mike, what are the units?
How many?
What are the units after 300?
That's going to be 300, it's not 300, it's 3,000. 3,000 millimeters per microsecond.
Thank you.
Okay, but you don't have to remember those. Okay, okay, yeah, okay. But just because of a greater speed in the tissue, what is it you will have? Yes, okay, you will actually, yes, okay, end up with a greater wavelength. Okay, whereas, for instance, okay, if you went to a tissue with a lower speed than that of soft tissue, for instance, let's say it's okay, let's say water. That's where you actually will have, okay, as a lower wavelength. Let's say it's okay, just 500 millimeters. And that is all, yes, okay, if you kept the frequency the same. Yeah, okay. But for now, guys, okay, as this number here is okay, 1.54 millimeters. Okay, is going to just okay apply for okay as a 1 megahertz frequency transducer. The remaining says okay, if our frequency was 1 megahertz, then the period was going to be 1 microsecond. Did that make sense?
So we just need to know that top value.
Exactly.
Got it.
Okay. Okay. Now some of you will ask, okay, as where does this 1.54 come from? Or 1.54 millimeters? My dear guys, just okay, this number here is actually as okay derived from the speed of sound in the soft tissues. Did you guys get that?
Yeah.
Okay.
I'm confused on the example you did about bone. What is the 3,000 versus the 2,000 or 20,000?
No, my dear. Okay. Don't get into that yet. Okay. But what you can say is okay, bone is going to be as okay, a more dense or more solid tissue compared to soft tissue. So that's why it's okay, we have a greater speed. Did that make sense?
Okay, that's the speed.
That's going to be you have a greater
Okay.
speed in bone
Because it's under
compared to
wavelength.
soft
That's why I
tissue.
was confused.
No, that's fine. That's fine. Okay. Once we get to as okay propagation speed of sound, that's okay. We can always talk about that. Okay. But here, this 1.54 is mainly as okay from speed of sound in soft tissues. And that's why as okay on page 33, it says in soft tissues with a frequency of 1 megahertz. Yeah, okay. The wavelength is going to be as okay be 1.54 millimeters. Did you guys get that?
Yeah.
Good. Okay. Now, guys, okay. If you go to page number 34, what you mainly will see is that, okay, there is a formula or an equation that says wavelength. Now, please keep in mind, guys, okay, this wavelength here is going to be as okay. We end up as okay calculating the wavelength in millimeters. Yeah, okay. Where you mainly as okay will see is going to be equal to and up here is okay, you see a fixed number, which is this. Or we can say it's okay, this much. Okay. Where this mainly as okay is, yes, okay, we can say it's okay derived from speed of sound in soft tissues. And that's going to be as okay, mainly as okay, divided by the frequency. That's your formula of deriving, okay, you can say it's okay, calculating the wavelength. So what we just said that, okay, yes, what's the wavelength? In soft tissues. Okay, where the speed is going to be as okay, this many millimeters per microsecond. For instance, okay, if the frequency was of the transducer was 1 megahertz. Now in this case, that's okay, that's going to be as okay, we can say okay, 1.54 divided by 1. Which is going to be, it's okay, 1.54 millimeters. Yeah, okay. Now this 1.54 is okay, standard if they talk soft tissues. Yeah, okay, because where did this 1.54 here come from? It is made as okay, taken from the speed of sound of the sound wave as okay as it travels through soft tissue. So that's going to be a standard. But then they may ask you, yes, okay, what is going to be as okay your wavelength? Yes, okay, of course, that's okay. Still, yes, okay, in soft tissue. So yes, okay, 1.54 is the standard. But that's okay if you had a frequency of a transducer, let's say it's okay 2 megahertz. Okay, now please keep in mind here, guys, that's okay. Your wavelength is going to be as okay in millimeters. Mainly because that's okay. The speed that you took here is if you okay calculate, okay, if you take the numerical value of the speed of sound and measure it in millimeters. Okay, but this is going to be the distance that the sound travels, the distance that the sound travels in terms of millimeters per microseconds, because okay, here we is okay, take the units in megahertz, which is reciprocal to microseconds. So the sound of speed in soft tissue or ahead of me is okay, 1.54 millimeters in 1 microsecond. Okay, but please be with that. Don't worry about that right now. The question is going to be, okay, what will be your frequency, or what will going to be your wavelength if you increase the frequency of your transducer from 1 megahertz to 2 megahertz? When it was traveling, when that sound wave was traveling through the soft tissue. And in this case, yes, okay, it is going to be 1.54 divided by 2, which becomes 0.77 millimeters. Okay, so whether you want to do the math every time, or this is mainly as okay, going to be a number that you may as okay, need to just remember that that's going to be as okay, half of this.
So we need to know 0.7.
But yeah, roughly speaking.
Okay.
Unless you want to, as okay, do the math every time. Because this is going to be as okay, a number that will come up again and again. Okay, but you can mean, yes, okay, just says okay. And you will go further and says, okay, what will be the wavelength? Of course, that's okay, measured in millimeters in a soft, it's okay, of a sound wave, that's okay, traveling through soft tissues. If we, for instance, okay, had, if the wavelength or if the frequency was 3 megahertz. Now, roughly speaking, my dear, that's going to be as okay, 0.5 millimeter.
So are these like the only ones we'll have to know?
Pretty much.
Okay, because I can't do math like that during a test.
No, my dear, you can go on with less, it's okay, limitless, but you can just say, it's okay, if you remove the decimal from here, you say, okay, you have 1.5 divided by 3, right? Clear?
Yep.
Good. Okay, now you can't divide 1 by 3, right?
Right.
Good. So that's why I said, okay, as to get rid of this decimal, you just write 0. Okay. You write 0, and okay, whatever number you will end up getting it. So now it's just mean, okay, 15 divided by 3. So what do? What's 15 divided by 3?
5.
5. Yeah, okay. But the main point that I just wanted to establish was that we can say it's okay. As our frequency increases, our wavelength decreases, right? Did you guys get that? Did you guys get that?
Yes.
Yes.
Good. Any questions? Okay. So please, please, please keep in mind that 1.54 is fixed. But please keep in mind that that's going to be as okay fixed if you talk about soft tissues. Because what we actually can say is that in different tissues, you will have different wavelengths. Okay, which is going to be as okay determined by the speed. Okay, so something which is not written in your book directly, but you can write it down. So that's going to be an increase in speed of sound. Okay, an increase in speed of sound will lead to an increase in wavelength. Is that clear? Okay. An increase in speed of sound will lead to an increase in the wavelength. But, and you can write that but with a big B, big U, and big T, bold, underlined, whatever, italic, metallic, whatsoever. An increase in the wavelength. Now we're just talking the other way around, right? An increase in the wavelength will not, and you can write the word not in capitals, lead to an increased speed of sound. Really simple. Did you guys get that? Okay, so it's only going to be yes, okay, an increase in speed, or we can say it's okay, a change of speed, which will have an okay, yes, directly change in the wavelength. If the speed increases, the wavelength increases. If the speed decreases, the wavelength decreases. Clear? Did that make sense? But it's not going to be the other way around. Did you guys get that? Any questions? Yeah, okay. Now, what I said in chapter 2, what we're going to be is, okay, I mean determining how fast or slow speed will travel. What was the main determining factor that will determine how fast or slow speed will travel?
The medium.
The medium. Clear? Okay. So what are we going to have? We're going to have, okay, different mediums through which the sound will travel, right? Clear? Okay. And those different medias or tissues, if you want to call it, are going to have different propagation speeds. Did that make sense? Okay, so those different propagation speeds through different medias will affect the wavelength. Clear? Okay, but the wavelength itself will not change the propagation speed. Because what determined this? Okay, that part of the wavelength that was made is, okay, the period. Okay, okay. I can say a word slowly. I can say it fast. But you can mean says, okay, the time that it will take between me uttering the word and it reaching to the ear is going to be determined upon the kind of medium that the sound is traveling through. Okay. Okay. So mainly because, okay, the sound's speed changes as it travels through the medium. It has its own effect upon the wavelength. Okay, the wavelength was also determined by the source, just because its relationship to the period and or the frequency of the transducer. Yeah, okay. So in a tissue with a greater speed than that of soft tissue, sorry. What will you have? You will have a greater wavelength. If the frequency of that transducer was the same, right? Okay. Okay. Although it's okay, that was the same frequency transducer, but because of a greater speed, the wavelength would be greater. Or if it was at a lower speed, all is okay produced by the same transducer, whereas okay, with the same frequency, with the same wavelength, with the same period. Okay, but that wavelength due to is okay, lower speed will have a lower wavelength in that tissue. Due to the lower speed, but not vice versa. So speed can affect the wavelength, but wavelength cannot affect the speed. Did that make sense? So here is okay, the relationship is one-sided. Okay, it's a one-sided relationship. You can say, okay, the speed may love the wavelength, but the love doesn't, or the wavelength doesn't love the speed. Okay. Or whichever way you want to take it. So that's okay. That 1.54, that is fixed for soft tissues. Okay, it may increase if we talk about a medium where the speed is greater than that of soft tissue. And if you divide that with, okay, as the same frequency, what will you get? A greater wavelength. Yeah, okay. So one thing that you will be tricked about is that they may ask you as, okay, something like this. What is the speed of sound in, let's say, it's okay, soft tissue? If the frequency of the transducer is 3 megahertz. Now, guys, please keep in mind here, it's okay. The speed of sound is going to be, it's okay, constant. And okay, yes, because it's okay, 1.54 meters per second. Or 1.54 millimeters per microsecond. Even if this transducer was a 3 megahertz, 10 megahertz, so and so. Yeah, okay, because the speed of sound is going to be determined by the nature of tissue and not the frequency of the transducer. Yeah, okay. Whereas if they is okay, change the speed of sound here is okay into wavelength, then you'll go and say it's okay. That wavelength was going to be as okay, our standard 1.54. Now it's okay divided by the frequency of the transducer. Now, if you said it was a 3 megahertz transducer, then that was going to be as okay 0.5 millimeters. If we said that okay was a 10 megahertz transducer, okay. Now 1.54 divided by 10. And anybody tell me what the answer will be?
You just move the decimal over, so it's 0.154.
1154. And what will be your unit here, my dear?
Millimeters.
Millimeters. Exactly. Did any of you get any of this? Okay. Now, hopefully that's okay. We'll get a little bit more clear. That's okay once we get on to just okay talk about the speed of sound in different tissues, where the median speed of sound is soft tissue. Okay, not too fast, not too slow. But actually, it's okay. We take the range of the minimum speed and the maximum speed. The speed of sound tissue is of sound in the soft tissue is somewhere in between those two extremes. Okay. Any questions? Now, guys, okay, just another point. You may write that, okay, as separately. That's fine. So you can say it's okay, the higher frequency. Or you can say it's okay, the greater the frequency. The shorter the wavelength. Okay, because they're inversely proportional, right? Okay, so the greater the frequency, the shorter the wavelength. Will be good for better diagnostic imaging. So what would that mean? That would mainly mean that, okay, yes, the higher the frequency of your transducer will give you, yes, okay, or produce sound waves with shorter wavelengths. Did you guys get that? And what those shorter wavelengths will give you is better diagnostic images. Okay. But please keep in mind, yes, okay, that good is good, but then too much good is bad. The too much good being bad, we will talk about that in chapter number 6. Okay. And that's why it's okay, your ultrasound transducer has an upper limit of the frequency, right? Do you guys remember that one? What was the max typical value for ultrasound frequency?
15 megahertz.
15 megahertz. Okay. It may go about that, but that's okay. What's going to happen? Yes, okay, too much good is bad. So something bad is going to start to occur. Clear? Okay. But why is it okay? Yes, that high frequency transducers or PSOK, GSOK, or we can call SOK, is going to be better for diagnostic imaging. That'll be something that we talk about more of SOK from chapter 10 and onwards for a couple of chapters. Okay, guys. Any questions? Yes, okay. Welcome to the intro about, yes, okay, what we call soft tissues. Okay. So just like we said, sound waves, wavelength is the only one of our 7 parameters that's going to be determined by not just the source, but the behavior. Then we can say it's okay. The greater the speed in the medium, greater wavelength. Lower speed, lower wavelength. Yeah, okay. But in soft tissue, that's okay. What was going to be is okay, your speed, 1.54 millimeters per microsecond. So that's from where you get 1.54 as the distance of the wavelength. Which is going to be as okay divided by the frequency. And please keep in mind here, guys, that frequency has to be expressed in megahertz. Clear? Okay. So if they gave you as okay a transducer with, let's say, as okay 10,000 kilohertz, you have to convert those 10,000 kilohertz into megahertz. And what would that be? 10,000 kilohertz is equal to how many megahertz? You don't necessarily have to just, okay, do that math in your head. You can use a rough piece of paper, right? So 10,000 kilohertz is equal to how many megahertz? Ten thousand kilohertz is equal to how many megahertz?
10. No, my dear, it's not 10. Anybody else? Ten kilohertz is equal to how many megahertz? Ten kilohertz? No, is that what you're asking? 10
No,
kilohertz?
that's not what I'm asking.
Okay, what
I
are you?
say, okay, 10 kilohertz. Okay, let me repeat my question.
Okay, thanks.
10 kilohertz is equal to how many megahertz? So you have 10 kilohertz. How many megahertz would you have?
0.01. If you have 10 kilohertz and you're looking for megahertz, it is. It's 0.01.
Yeah, that's what I got. I thought you said,
You're
not
asking 10
bad.
or 10,000?
Well, at first I thought he said
You have 10
10,000.
kilohertz.
Yeah.
So translate 10 kilohertz into hertz. If that makes it easier for
Into
you.
hertz or megahertz?
Whichever. Whichever makes it easy for you. OMG. Guys, you may have to spend your Christmas vacation in school for your quiz.
Can you say like I got 0.01 again. How's it not that?
You got, what did you get?
0.01.
0.01, which is the same, which is correct.
That's what we just said. Okay.
No, you said 10.
Teresa just said 0.01.
Are you sure?
I'm 100%
Like 5 times.
We'll run the
Okay,
recording
sorry,
back.
okay. Maybe it's okay. My frequency is okay. Sorry, yes, okay. 0.01 or 100th of a megahertz, right? Did that make sense? Clear? Okay. Okay. But yes, okay, those are things that you have to, yes, okay, keep in mind. Okay. Okay. Now, so far, so now, guys, okay, anybody who is in the least doubt about the relationship between period and frequency. Okay, relationship between period and wavelength. Period and wavelength are yes, anybody. Period and wavelength are
Directly
Directly
directly proportional, right? Okay. Okay. Wavelength and frequency
inversely.
inversely. Okay. Are they reciprocal? Are
No.
wavelength and
Okay.
frequency reciprocals?
No.
No, they're not. They're only inversely proportional. Okay. Okay. So greater the wavelength, that's what I mean. Yes, okay. The lower the frequency, the greater the wavelength, or vice versa. And when we say frequency, yes, okay, what are we talking about? Yes, okay, the frequency of the sound wave, right? Okay. Okay. Which is going to be produced by the transducer. Yep. Okay, guys. So just remember this one here from now that, okay, yes, wavelength is the only of your 7 parameters determined by both source and medium. Okay. As far, okay, the source is concerned, what's going to, okay, be the main factor there, the frequency of that transducer. As far as the medium is concerned, what's going to be, okay, the main determining factor there, the speed at which the sound travels. Clear? Okay. Okay. But that speed of sound in the medium going to, yes, okay, be related to the frequency? No. Is that clear? Okay, which mainly means that, okay, yes, you can use a 2 megahertz transducer and a 5 megahertz transducer producing sound waves with each of their own frequencies, right? Okay, one is 2 megahertz, one is 5 megahertz. But as far as, okay, the speed of that sound traveling through, yes, okay, let's say it's, okay, the same medium. Let's say it's, okay, you have boom. They will be traveling at the same speed. Why? Okay, because that speed is only going to be determined by the medium. That's fine. Take a 15 minutes break. I see you guys back at 11:05. Or let's say 11:10. That's fine. 11:10. Please read on your wavelength. Okay. And if you still have any questions, that's okay. Feel free to ask when we get back. Okay. If not, we can go on to the next fellow. Sounds like a deal? Goody buddy. Any questions, guys? No? So how many kilohertz do we have in 10 megahertz? How many kilohertz do we have in 10 megahertz?
0.01.
0.01. How many kilohertz do we have in 10 megahertz?
10,000.
10,000. Just give me a second. Sorry for a second. Okay, guys, sorry for that. Okay. Okay, guys, now let's just go back and talk about what we'll call is, okay, or three bigness parameters. Okay, guys? Clear? Okay, so we'll talk about our three bigness parameters, and you'll find those from page 27, I hope so. So the three bigness parameters, and I just take them in a little bit different sequence, is going to be power. Intensity. And last one is going to be amplitude. Okay. Now, guys, the reason that I take it in this way is that, okay, because these two here mean that's okay, but are going to be as okay, we can say it's okay. Measurement of the amount of energy, or to be more specific, sound energy, or also is okay known as acoustic energy, that the sound wave will carry. Whereas, okay, yes, the amplitude is just going to be how big, or for that matter of fact, yes, okay, small is it that the sound wave will be. Or upon, all dependent upon the power and the intensity and that the sound wave carries. So one thing that is okay that we will be able to, yes, okay, at least should be able to establish now is that, okay, yes, these three bigness parameters here is okay are related to one another. Is that clear? Okay. Now this bigness here, if we talk about it's okay, the bigness itself. Okay, because okay, what is that? Ultimately, it's okay. Will determine is it's okay. How big or small is it that the view will be? So this bigness here is okay. Can also be referred to as magnitude of the waves. Okay, but usually it's okay when we say magnitude, it means it's okay. It just talks about it's okay how. Means okay how big is it that substance or a thing will be. Did you guys get that? Yeah, okay. But at the end of the story, it's okay. At the end, it's going to mean it's okay be determined upon how much power does the sound wave have, which will relate to it's okay how much intensity the sound wave will have, and that will determine whether we have okay as a big sound wave or cycle, or it's okay small sound wave or cycle. Where we can say it's okay, this one is going to be it's okay a greater magnitude. Whereas okay, this one here will be it's okay lower magnitude or amplitude. Did you guys get that?
Yeah.
Good. Okay. Now, guys, just to, yes, okay, kill one, yes, okay, I kill, I leave, you can say, okay, 3 birds in this case, yes, okay, with 1 stone. Okay. These 3 bigness parameters here. Okay. Are controlled by the source. Oh, let's say it's okay. Let's say not source. Let's say it's okay. Let's put it by the what we actually it's okay. We'll call power output. Which later on, yes, okay, will go under, yes, okay, and a whole bunch of other names. But we can say, okay, a caustic output. And so on, so on, so on, so on. Okay. But okay, what we'll find on our ultrasound system is that there's going to be, yes, okay, a knob that will say, that says power or power output. And that's pretty much okay as we're our bigness parameters of the sound waves will be controlled. Okay, so let me just write it again so you guys have it on black and white. It says, okay, the bigness parameters are controlled by, or we call it, okay, the power output. And where do we find this power output? On the ultrasound machine. Okay, guys. So if you look at, okay, you can say it's okay, your keyboard, or if your ultrasound machine, where you actually is okay, will have okay, yes, or may look like okay, a regular keyboard for your computers, but here's okay, you have the tabs with the letters and numbers and so on. So, okay, there's going to be as okay a knob over here that we'll talk about in chapter number 4. There's going to be as okay, most systems will have okay as 4 knobs here. We'll talk about those respectively in chapter 10, 14, and 19. But most systems over here will have a knob, which is going to be as okay, your power output knob. So, okay, which you mainly okay, see as okay, that okay, yes. Now just keep in mind that these are going to be knobs that okay, yes, if you turn it, let's go, yes, okay, clockwise. If we did, that will actually lead to increase. In this case, that's okay, increase in the power output. Whereas if you turn this clockwise knob here, okay, sorry. What we used to call anti-clockwise. Some people may also call it counterclockwise. And in this case, that's okay, that's going to reduce the power output. Clear? Did you guys get that?
Yes.
Okay. We can make it okay by changing the power output. That will change the intensity, which of course is okay also is okay relate to is okay a change in the amplitude. Did that make sense? Okay. But pretty much okay as the power, the intensity, or the amplitude of the sound wave that this it's okay. Because it's on me, it's okay, the energy that is going to be as okay. Ultimately as okay be emitted by the transducer. Okay. So in most systems, in the upper left-hand corner of your keyboard or console, if that's what you want to call it, is going to be as okay, this power output knob. Clear? Okay. And whenever you have a knob that you can twist and turn on, clockwise is always going to be increased of whatever function it is. Counterclockwise or anti-clockwise is always going to be decreasing that function controlled by that specific knob. Did you guys get that? But we can mainly say, okay, by changing the power, we also change the intensity, which is going to change the amplitude. Now, how that works out, well, okay, yes, we can always talk about that. But let's just talk about each of these three bigness power or the bigness parameters here, one by one. So our first bigness parameter that we'll talk about is going to be power. Is that clear? So the first bigness parameters that we'll talk about is going to be power. Now, what is power? Now, some people may define it as because it's the rate of transfer of energy. Clear? Or you can also say it's the rate at which work is performed. Now, guys, just out of context, but does anybody know it's how do we define work?
Is it when you like use energy?
Okay, good. Good. That's just one part of work, or one of the requirements of work. So we can say, when energy is transfers, that's used. 2. What comes here? Let me put it this way. Somebody have something in their backyard that they need to move.
Is it over an area?
Okay. So work will only be done if, okay, as energy is transferred. Now, as okay, some of you may have a big rock in your backyard that you want to move, right? Yeah, okay. You can hire a handyman or whatsoever, whatever you call him or her, to come and move that thing. Now, what he or she may be doing is, okay, transferring a lot of energy onto that rock. But if that rock is not moving, then the work is not done. Yeah, okay, so in terms of physics, yes, okay, what do they call work? When energy is transferred to move an object. So the movement is must. Otherwise, it's okay, I'll be just standing there, it's okay, and pushing and pushing and pushing and pushing onto that rock. Okay. You may see as okay, somebody pushing onto that rock. What a physicist will see is the transfer of energy from person onto rock. Now the question is going to be is okay, if that is that energy enough to move the rock, then work is done. If not, then work is not done. Did that make sense? And that's where as okay, machines comes into the equation. Yes, question. What's a machine?
It's hard to define.
It's hard to define. Okay. Just define it in soft words.
Something used to, carry out a procedure, pretty much, to make
Okay.
something.
Okay. Let's just put it this way, right here. Maybe I can help you on the way to define as okay. Let's say that okay, as you were to do or perform a certain task and you didn't have a machine. Could you still do that work?
It depends, but yeah.
Literally, you could. Okay. But what was going to be the difference between yes, okay, doing that task with a machine versus without a machine?
It's going to require a lot more work.
Is going to be as okay a harder task. So what is the main goal of a machine?
Improve efficiency.
Or make it easier to do, right? Did that make sense? Okay, now does anybody know the first machine that man made? Or we theoretically as okay thing is the first machine that man made?
Is it a wheel?
Wheel is an invention, my dear. Actually, a lever. Anybody know what a lever is? Not lever. Oopsie. Oh, that's probably just okay, too big. Shit. Sorry. something here that needed to be moved. Whatever shape, you can make it this shape here. And what they said was, okay, it was going to be easy to make it move if you bring something here and then push on this thing here. That's what you call a lever. But guy, yes, okay, in terms of physics, yes, okay. Work is only said to be done if, okay, as if energy is transferred to make an object move a distance. Shorter or longer, that is going to. Did that make sense? Okay, guys. Now, what it mainly is, okay, is going to be as okay, rate of transfer. Well, okay, yes. You can also say, okay, how slow or fast is it that, okay, as the energy was transferred to this rod to transfer it onto, yes, okay, let's say this log here that might then start rolling over 7. Clear? Okay. The more energy that was used, or yes, okay, transfer onto, yes, okay, this lever here, that's going to, yes, okay, determine the rate. Okay, but you can say it's okay, we don't want to go, because that's going to be, yes, okay, how fast or how slow. Okay, but most likely it's okay, we can mean it's okay, also say it's okay, the amount of transfer of energy. Okay, is going to be what you can call is okay, the rate of transfer of energy. Okay. Now, guys, in this case, it's okay, our unit for power our unit of power is watts. Just think of it in this sense here, guys, as okay, yes, because it's okay, 100 watts bulb. Now, since we has okay, just mentioned yes, okay, talked about our rate and so on, so we can say okay, this 10 unit, 100 watt units bulb here versus, let's say it's okay, 1,000 watts bulb. Did that make sense? Clear? Okay. Now, just to put it this way, let's just assume, because okay, that this 100 watt bulb here is okay, produces brightness or what you can call it. Okay, a unit for brightness is lumens. Okay, because that says okay, 100 lumens. Okay, where okay, the lumens produced by us, okay, 1,000 watt bulb, because that's going to be 1,000 lumens. The remaining can say is okay, that of course this here 100 lumens is going to be as okay, we can say it's okay, a lower brightness of the bulb compared to as okay, the 1,000 lumens, which is going to be as okay, a greater brightness. Or we can actually say that okay, as the brightness of 10 100-watt bulbs is going to be as okay, providing us okay the same lumens of brightness as 1,000-watt bulb. Did you guys get that?
Yeah.
Right, okay. So we can actually say that okay, this one here is going to be as okay equal to as okay 10 100-watt bulbs. Clear? Okay. But then of course, well, okay, what's going to happen? In this case, okay, especially okay, when we talk about lights and bulbs and so on, so you will also as okay be increasing your electricity used like usage 10 times. If you replace all your 100-watt bulbs with 1,000-watt bulbs. And of course, yes, okay, your electricity bill may yes, okay be increased 10 times as well. So your bill, which might used to be as okay $400, may now become $4,000. Did that make sense? Right, okay. Why? Because you can say, okay, per hour that you have okay as a bulb on, if you use 100 watts, that's okay. If we just use okay, it says okay, 100 watts in an hour. Well, okay, as if you had a 1,000-watt bulb on, it's okay, it may use as okay 1,000 watts in an hour. Did that make any sense? Okay, but of course that's okay. 100-watt bulb is going to have okay produce less light energy compared to a 1,000-watt bulb. Because that's okay, 1,000-watt bulb uses more energy than a 100-watt bulb. But of course that's okay. That's going to cause that okay as your electricity bill may be increased. Clear? Okay. But you, on the other hand, can also say, well, okay, yes, I can produce the same amount of brightness by just using as okay 1,000, okay, a single 1,000-watt bulb that might have required as okay used as okay 10 100-watt bulbs will produce the same brightness. Did that make any sense? Did you guys get that?
Yes.
Okay. But that's okay. Here we can mean it as okay the power of that ultrasound wave is mean as okay going to determine as okay how much energy will it carry, or it be less energy, or it be more energy. Which means it will mean as okay you will have okay as a low power or a greater power. Yeah, okay. The unit of your power is going to be watts. Okay. Now, although it's okay in ultrasound, we're not going to use watts. It's going to be fraction of a watt. Clear? Okay, so actually it's okay in milliwatts. But you can say it's okay, 1 watt divided into 1,000 equal parts. Each part is going to be a milliwatt. Clear? Okay. But as far as the typical value here is concerned, Hakuna Matata it. Clear? Okay. So you don't know you don't need to remember or memorize or even bother about the typical value of your ultrasound waves here. Is that clear? Okay. It's just mentioned because okay, that's how it's okay. The format of okay, the info in this chapter here is concerned. But you don't need to remember it. Did you guys get that? Okay, so I'm not going to be asking you, okay, what's the typical value of the ultrasound waves or power, sorry. Yeah. Next one. Now this one here is important. This fellow here is important. Determined by. Now I already told you 90% of it. Because what did we say that okay, I was going to determine your power? The source. Clear? But please, 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 please. Mind it here, girls, or guys, sorry, that your source in this instance here is not going to be the transducer, but the ultrasound system. Did that make sense?
So
Okay, so
power
power,
is determined by the source, and in this case, that's the ultrasound system.
exactly.
Okay.
Okay, okay. Now, well, okay. Did that make sense? Clear? Okay. Now the second part will come. Okay, the second part of okay as determined by is okay as mentioned in your book. We'll come back to that in just a second. But let's just say as okay, is this thing here is okay adjustable? Is your power adjustable? And the answer to that is yes. Why yes? I just told you guys that because we have a knob that we can twist and turn that may as okay increase the power or decrease the power. And that mainly mean that's mainly as okay what you mean by being adjustable, right? Did that make sense? Just like as okay the temperature in your house. Can you adjust that? Okay, yeah. Because yes, okay, I guess okay, most of your houses will have what you call as okay a thermostat. Clear, okay, where you can set a temperature and okay, yes. Your heat or air conditioning system is okay, may turn on or off accordingly to your settings, right? Okay. Did that make sense? Okay, so it says okay, the room temperature, the room in which you are sitting in, that's okay. You can adjust the temperature of that. Mainly as okay by setting your thermostat. Or just like okay, as setting the temperature on your microwave or stove or whatever. Adjusting is okay the volume of the music playing in the background. Okay. Did you guys get that? Okay. So your power is adjustable. How? Mainly as okay by adjusting the power output knob. So you increase that, what's going to cause? That okay, as your ultrasound, okay, you can say that your system. Now technically, it's okay, what you do by, let's say, it's okay, increasing the power output is that you send a stronger electrical signal from your ultrasound machine towards the transducer. Did that make sense? Okay. It's ultimately as okay going to be as okay the job of your transducer to convert that electrical energy into sound energy. Did you guys get that? Okay. Now how and so on, not really how. But it's okay, what is it that the transducer has that enables it to convert that electrical energy into sound energy? We will talk about in further details about that in chapter 8. Clear? Okay. But you, yes, okay, on the ultrasound machine sets the power, or you can say, okay, the amount of energy that is going to, yes, okay, be transferred from the system to the transducer. And the transducer just has to convert that into that electrical energy into sound energy. Did you guys get that? Okay, that's why it's okay. The transducer itself cannot determine the amount of energy. It's going to be determined by the system. But who sets it? It's you, because it is adjustable. Did I make myself clear? Okay, or let's put it this way. Somebody tells me, who wants to be the sonographer here? Who wants to be the sonographer?
Sure.
Okay, Caitlin, you are the sonographer. Clear? Okay, and you say, Mike, what we want you to do for the next test is bring in, okay, that's a box of candies. Now you're going to be the one who are mainly as okay, determine as okay, how stingy or how generous I can be. Clear? Okay. By setting as okay, that amount of candy try to be low, and that makes me stingy. Or as okay, high, which is how to as okay, I have to be generous. Okay. Now I may not bring in box of candies, but I may bring in money. Okay, so you may say, okay, Mike, you got a yes, okay, bring in yes, okay, $100. Now that's the amount of yes, okay, energy that I bring to the class. Now who wants to be the transducer then? Anybody wants to be the transducer?
I will.
Okay, so Caitlin said me as okay to bring in $100. That's the amount of that's okay electrical energy that I will bring to the class. Now, Christina, you are the transducer. What I will do is give you these $100 and say, okay, well, here, dear, here are $100. Now, that's okay. Just produce, that's okay. Convert these $100 here into chocolate pieces, which is going to be the sound wave. Did that make sense? Right. Okay. But Christina, without you getting those $100, you will not be able to produce the pieces of chocolate or whatever, or buy the pieces of chocolate. Clear? Okay. Who brought in those pieces? I said, okay, $100. I did. But who told me to do that? I was a stenographer. Clear? Did that make sense? Clear? Okay. So that's how it works. So, Christina, you may not be able to work if it's okay. I didn't give you the $100 in form of energy, which was determined by Dr. O'Brien. Okay, so that's why here we say it's okay, determined by the source. Or you can say ultrasound system and not the transducer. Did that make any sense? Good. Now, guys, yes, okay. In power, if you look at, okay, determined by, and okay, if you look at the second paragraph, can anybody read that out for me? In the box that said determined by, the second paragraph.
Sure. Go ahead.
Okay, okay.
Okay. The rate at which power decreases as sound propagates depends on the characteristics of the medium and the wave.
Good. Now, guys, what does that mean? Now, the main word here is decreases. Decrease is the major term here, okay? Clear, okay? Okay. So what's going to happen to the sound wave as it travels through the medium? Its power will decrease. Is that clear? Okay. So as the sound wave travels through the medium, now what's going to be our medium here? In ultrasound, your tissues, right? Okay, but what will happen to its power? It will decrease. Did you guys get that? Okay. Now we can say, okay, the degree, oh, yes, okay. The rate at which this decreases, what is okay, the rate at which the power decreases is going to be determined by the nature of the medium. Did that make sense? Now let's say as okay, we from those $100 were able to buy us okay 1,000 pieces of chocolate. Okay. Some of you guys may be walking home on that day with yes, okay, cavities. But let's say that that's the amount of that's okay, the pieces of chocolate that we were able to buy by those $100. Now, what is it that you guys are going to be? Let's say it's okay, you are different tissues. Did that make sense? Now, yes, okay. Christina as okay as a as okay as a transducer says okay, well, I got enough money to produce 1,000 pieces of chocolate. Now, Christina, you probably not going to be able to okay take any chocolates. That's fine. Okay, no chocolates, no cavities, no sugar rush. The remaining guys here in the group, and Kathleen, neither are you. So that's okay. The two of you, yes, okay, no cavities, no sugar rush. But whoever is left, Teresa, Christian, Lillian, Angeles, and Jennifer, are different tissues. Now, what does it mean to be different tissues? That's okay. They're going to, that's okay, cause a different decrease in the amount of the power. Or let's say that's okay, amount of pieces of chocolate that's going to be remain in the bowl once they have got their hands into that bowl, right? So somebody with a big tooth or sweet tooth, what is that going to cause? Once he or she gets his or her hands into that chocolate ball, a greater number of pieces of chocolates will be gone. Did that make sense? Okay. But this here actually is okay, is just an example of okay, what we call an acoustic propagation property. Because what did we say an acoustic propagation property was? As the sound propagates or travels through the medium, the effect that that medium had upon the sound. Did that make sense? Any questions? So those of you with a sweet tooth, once you get your hands on that chocolate ball, that's okay. A lot of pieces of chocolate are going to be missing. Somebody will say, well, okay, I already got enough chocolate left over from Halloween and Thanksgiving. And more is going to be collected, yes, okay, during Easter and New Year and Valentine's Day. So that's okay, I'm good. I'll just take a piece or so for now. Okay. But that's okay. You can say it's okay as the sound travels through different media. That's okay. What's going to happen? That power of that sound wave will decrease. The juicy detail, the further details about that's okay. This decrease in power is something that we talk about in chapter number 6. Okay, but what we call this decrease is what we refer to as attenuation. 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 So that will mainly be yes, okay, what we in this case, at least for now, I can say yes, okay, will be the decrease in the power. How and when and where? Yes, okay, when that sound wave travels through the medium, it's going to lose its power. Just as I say, it's okay, a big boom being produced somewhere. The people standing right next to it will be able to hear clearly and loudly. Whereas, okay, at that distance, that's okay between the place where that boom occurred and okay, as some people standing at a greater distance, that's okay, they may not, that's okay. The sound's intensity is going to get lower and lower and lower. Mainly because that's okay, that sound travels, that's okay, it actually is okay, it attenuates. So beyond a certain distance, that's okay, you may not be able to, or you would not have heard anything. You have been unaware or ignorant of okay, that big boom that just occurred. Did that make any sense at all?
Yeah.
Okay, guys. Now just take your lunch break, and when we get back, guys, we'll talk about yes, okay, our next bigness parameter, which is going to be intensity. Clear? Okay. So I will see you guys, should I say, at 1 o'clock. Is that a fair deal? Okay, guys. Have fun tonight. Okay, guys. Welcome back. So where were we? So far, any questions about power?
Can I just clarify something?
No problem at
We
all.
we don't need to know the typical values, right, for power?
No.
Okay, thank you.
Just remember its unit. Clear?
Got
Okay.
it. Yep.
Okay. So watts. And easy check, that's okay. Just remember it's okay, the watts of your bulbs. That's the power. That's going to be as okay, the amount of energy that they use per is okay, any unit of time. Clear? Okay. Did that make sense? Okay. But
Yep, thanks.
you can say as okay, the greater watt bulb you use will use more energy. Clear? Okay, and this energy is okay in case of a bulb is going to is okay cause greater brightness. Did that make sense? Right, okay. Okay, so even yes, okay, in ultrasound, guys. Now later on, yes, okay, when we start talking about yes, okay, how the images and so on, so are produced, you're mainly going to see that okay, yes, more energy will produce more brightness. Lesser energy will lead to lesser brightness. Did that make sense? Okay. Okay, guys. Now let's just go on to yes, okay, our next bigness parameter in the row, and he or she is going to be intensity. Okay. He or she is going to be the intensity. Now, what is going to intensity, or what is it that intensity is going to be? Now, it's going to mean that's okay. We can say it's okay. It's going to be the concentration of power per area. Or mainly as okay as your book says, if you look at it, you says okay, the concentration of, that's okay over here is okay, just can call this okay, energy. Okay. In a sound beam. Now girls, or sorry, guys, sorry. Primarily, that's okay, the main reason that we end up as okay calling a sound beam will be brought as okay, it's going to it's okay be clarified in chapter 9. Okay, but mainly as okay at any point as okay we talk of a sound beam. that sound beam is going to have, okay, as a certain cross area. Yeah, okay, so if you find that's okay set here, let's just mark this one here as 1. That just says, okay, this is 2, or this is 3. Yeah, okay, just okay. Shit. Okay, that's fine. I can always remake the beam. If I says, okay, say, okay, yes, this here is your beam. So at this point here, the beam is going to have, okay, as a certain cross area. We can say as, okay, at point 2, the beam is going to have, okay, as a certain cross area. And we can even say as, okay, at point 3, for instance, okay, the beam is going to have a certain cross area. Okay, so the intensity mean is going to be as, okay, how much energy is distributed in this cross area, this cross area, this cross area. Why do they say it's okay in terms of it's okay in a sound beam? Because okay, what we'll talk about is okay specifically is okay in chapter 9 is that okay as your sound waves actually is okay starts behaving like a beam, just like a beam of light. Okay, but throughout is okay what remaining can say is okay the concentration of the energy in that beam at any point is going to be as okay, right? Is going to be as okay the intensity. Okay. Now we may as okay talk in further details about as okay intensity, intensity, intensity. And yes, okay, in terms of a beam, yes, okay, in chapter number 5, which is going to be as okay chapter on its own, mainly as okay, just talking about intensity and the types of varieties of intensity. Yeah, okay. Any questions so far? Okay. Now, no matter where in the beam you talk about, but as okay, what we actually is okay, we'll have in the center. That's going to be as okay, there will be as okay, a maximum intensity. Okay, where okay, as the intensity is going to get lesser and lesser and lesser as we go away from the center towards as okay, the periphery of the beam. Okay. Now, and that's why I made as okay, start talking first of as okay, unit of as okay, power versus area, because to as okay, know what the intensity or what the unit of your intensity is going to be. Just look at the definition here. Concentration of power over area. So what is the unit of power? We just said that, right? Okay, so that's going to be as okay, the unit of intensity, no matter in what context or what kind of intensity we're talking about. It's always going to be as okay, the unit of power, which is watts per unit of area. Or area, sorry, which was any unit of distance squared. Did you guys get that? So no matter which subtype of intensity we talk about, SOK unit is always going to be SOK, the unit of power by unit of area. Any questions so far, guys? Any questions so far?
No.
You good? What about the girls? What do they have to say?
Good.
You good? Good.
Yep.
Let's just then look what's next. Okay, now we can, it's okay, let's do our boxes now. The typical value, guys, well, okay, yes. If you want to, yes, you can remember, otherwise not really, yes, okay, must necessity. Clear, okay, but what was it? It was going to, yes, okay, be 0.01 to 300 watts per centimeter square. Okay. So anything between, yes, okay, 100 of a watt per centimeter square to 300 watts per centimeter square, yes, okay, that can be, yes, okay, the intensity of the ultrasound beam. Okay. Now let's put it this way, it's okay. As it's okay, what determines the intensity? Now, guys, that is going to be same as power. Did you guys get that? Okay. And what determines the power? Your power output. Did that make sense? But let us just put it this way and say, yes, okay, we have a, shit, sorry. We had, okay, as the power output. What was that? That was, okay, that knob on our system. What could that do? That could set, okay, as the power. Yeah. Power of what? The power of the sound wave. Which mainly, yes, okay, also is going to, yes, okay, set our intensity. Did you guys get that? Okay, now what I said earlier, yes, okay, that if you, for instance, okay, twisted that power output knob here clockwise, or okay, that was going to, yes, okay, increase the power output, right? Which means, yes, okay, we'll increase the power. which mainly is okay, will increase the intensity. Whereas, guys, if you went the other way around and turned the clock anti-clockwise, that was going to just, okay, decrease your power output. Okay, which means that's okay, would decrease the power, which would decrease the intensity. Did you guys get that?
Yep.
Clear? Okay. Now, as we also said earlier, that, okay, yes, the more and more and more and more and more that sound wave, yes, okay, will travel in the medium. Or what did we say happened to the power? That power will decrease further, 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 and further as the sound wave traveled deeper and deeper and deeper and deeper, coming across more and more and more tissues. Clear? Okay. Did that make sense? Did that make sense, guys?
Yep.
Good. Okay, whichever power we have set it on. Ultimately, as okay, what's going to happen as okay, that sound wave travels, it's going to just okay lose more and more and more and more and more of its energy. The power is going to just okay get lower and lower and lower and lower. Well, guys, the very same thing is okay will also is okay happen to the intensity. Clear? Okay, so as we go deeper and deeper and deeper and deeper, that's going to as okay, the intensity that we started off with is going to get lower and lower and lower and lower. But even if we just okay didn't talk about this thing here, because that's again just going to be okay the effect that the media has upon the power of the sound wave, and likewise that's okay the intensity of the sound wave. But if you just look here at this relationship here, what did that tell you? That what is the relationship between power and intensity? When one increases, the other increases. When one decreases, the other decreases. What do you call that kind of relationship?
Directly
Proportional.
Directly proportional, right? Okay. Did that make sense? So by increasing your power output, what do? Yes, okay, you increase the power of the sound wave, sound beam, whatever you want to call it. Okay. And what that is going to do is going to just okay increase the intensity. If you reduce the power output, you reduce the power of the sound wave. That's going to just okay reduce the intensity of the sound wave. Or yes, okay. If some of you were clever enough, you should already have figured that relationship out. Right here. Because what was it that your power was in your equation? It was the numerator, right? Did that make sense?
Yes.
Clear? Now, not just enough with that, guys. But it's okay, we just look at our equation and say, yes, okay. Intensity is okay, where was it? It was equal to power over area. We could say, yes, okay, which will mean going to mean that, okay, yes, whatever unit of power, which is watts, milliwatts, kilowatts, whatsoever, it doesn't matter. Okay, by unit of area. Sorry, which is going to be, sorry, which will be any unit of distance squared.
Mike.
Yes, my dear.
So, if we get a question that wants us to do like the intensity formula, and one of the options is like area, but it's not squared, would we have to square that so we could do the
No,
equation?
no, no, no. Well, okay. It is going to give you, yes, okay, the area.
Okay, thank you.
Okay. Okay. And if it's not squared, then okay. You probably ain't going to, yes, okay, have to square it out. Okay. Okay. So it is going to give you the area and says, okay, you can say, okay, it says, okay, area of beam, for instance, is 2 centimeters square. Did that make sense?
Yes.
All 4 or 5. Now, guys, what we just says, okay, just established from this equation here was that, okay, yes, our intensity is okay, that was going to be, okay, directly proportional to the power, right? Okay. Which mainly meant that, okay, yes, if the intensity increases, the power will increase. Okay. If the intensity decreases, then of course, yes, okay, the power will decrease. And that's mainly because we just established that, okay, yes, intensity and power were directly proportional. But as I say, yes, okay, that you should have been able to, yes, okay, figure out already, yes, okay, when we looked at the equation, because in the equation, yes, okay, your power, that was the numerator. Now then, guys, okay, as our next question is going to be, yes, okay, because in the equation here, what do we have? We also have a denominator. And what is that denominator? That is intensity. So, guys, that is always going to, okay, your area. And in this case, yes, okay, your intensity is inversely proportional to the area, which mainly means that, okay, yes, if you have a beam with a small area, now please keep in mind, yes, okay, that your power got to be constant. You will have, okay, as a greater intensity. So let's say, okay. So lesser area, yes, okay, that's okay, shit. A lesser area is going to give you, yes, okay, a greater intensity. Whereas, okay, yes, if you go by a bigger area, you will have a lower intensity. So that's okay. If you want, just okay, establish the relationship between intensity and power. You got to keep your area constant. And vice versa. If you want to establish the relationship between intensity and area, you got to keep the power constant. So let's just say, okay, establish this. Let's say that's okay. Okay. So here we have, okay, as we can say, it's okay, 2 powers. Although it's okay in the same area. Let's just assume that, okay, this here is an area of, okay, 4 centimeters square. Where here, we can say it's okay, our power is 12 watts. And here's 8 watts. Well, let's just do the 16, that's fine. So here is okay, the formula goes 16. Here goes 8 divided by 4. So in this instance, here's okay, what do we have? 16 divided by 4 is 4. 8 divided by 4 is 2. So what do we have here? It's okay, the intensity is going to respectively be as okay, 4 watts per centimeter square and 2 watts per centimeter square. Where we can say it's okay, here we have a greater intensity, mainly because of a greater power. Whereas over here, we have a lower intensity Y. Oh, sorry, we have a lower intensity Y, mainly as okay due to a lower power, which mainly as okay establishes that okay as power and intensity were directly proportional. Yeah, okay. But likewise, we can also say that okay, yes, that okay, and now we have, we want to establish a okay, relationship between intensity and area. Okay, so we can say it's okay, area and area. And let's just say that okay, here we have an area of 8 square centimeters, for instance. Versus let's say it's okay, 16 square centimeters. Okay, when both instances, okay, we gotta keep the power constant. That's okay, the power here and okay, the power here is going to be the same. We can say it's okay, 4 watts. So our first example here is going to be it's okay, 4 watts over an area of 8 centimeters square. Where here it's going to be as okay, 4 watts or an area of 16 centimeters square. Now, I may be a little bit off, but anyways, because you can say it's okay, 4 divided by 8 is going to be equal to a half. 4 divided by 16 is going to be a quarter. But what we mainly as okay just can say is that okay, as here we have a low intensity, mainly because of a great area. Compared to over here, it's okay, we have a greater intensity, mainly as okay, sorry, due to a smaller area. Which mainly as okay establishes that okay, yes, intensity is inversely proportional to area. Did that make sense? Did you guys get that?
Yep.
Okay, so what you see is okay in a sound beam. Let's just do it. What do you see? The area changes. We can say it's okay, we took it at different points and says okay, let's say it's okay, point A. We can say it's okay, point B. And we can find this okay, say point C. Although it's okay, it will be it's okay the same amount of energy that will be transmitted. But it's okay at point B, for instance. What is it we have? We have okay, it's a smaller area. Which will mean that okay, as we will have okay, it's a greater concentration of that energy being transmitted as compared to over here. Because it's going to be it's okay, a bigger area in which okay has the same amount of energy is going to be distributed. Okay. So at this point here is okay where your beam is narrowest. It has okay as the highest intensity. Mainly because of the narrower area. Or you can put it this way and say, it's okay, we have a hallway that gradually as okay gets narrower. Okay. And we have okay, let's say it's okay, there are let's say it's okay, 10 people, yes, okay, walking shoulder to shoulder through that hallway. At this point, here's okay, there's going to be okay a greater distance between the persons. Which means okay, the concentration of people in this area here is going to be lower. Where okay, at this point here's okay, they may have just okay squeeze pretty much okay right pretty tight up against one another. to be able to process, 10 people through at the same time. That means that, the concentration of people here is going to be greater. Yeah, okay, all these people, yes, that was mean, yes, just the power. Okay, well, the cross sections here, that was going to be, the different areas. But even if you don't want to go into all that, you can just look at the equation and say, well, intensity is the thing that we wanted to calculate. It's always going to be directly proportional to the numerator and inversely proportional to the denominator. Clear? So if you keep power the same, but changes the area, then as the intensity, which was mainly as what we calculate here, is going to be inversely related to the change in the area. So if you increase the area, the intensity will decrease. Or if you decrease the area, the intensity will increase because they were inversely proportional or inversely related. Clear? Whereas, if you keep the area constant, but change the power, then that is going to be directly proportional to the intensity. Clear? Okay. Whereas, as if you change both of them, well, as the final power contra your initial power is maybe dependent upon is which of the two parameters you increase, which of the two parameters you decrease when it comes to power and area, right? And all it also is how much is it that you increase one and decrease the other? Or how much is it that you may increase both or decrease both? Clear? Okay. So things like that, yes, that's what you may come across, yes, once we start doing the questions in the exercise. But if you remember this much, that power is directly proportional to intensity, and intensity is inversely proportional to area, yes, you can't go wrong. Okay, guys? So what I said, pretty much, it's on day one. Whenever you have an equation like this, where, a thing needs to be calculated by formulated in as with a numerator and denominator. That factor, that parameter is always going to be directly proportional to the numerator and inversely proportional to the denominator. Just as we said earlier when we talked wavelength, what was our formula to calculate wavelength? That fixed speed, right? For soft tissues, right? Okay. They want to be gentle with you guys, so it's that's why. They only talk of soft tissues. Okay. But what was that going to be? It's it was going to be divided by the frequency, which in that equation then became the denominator. So what did that tell you? That frequency and wavelength were inversely proportional. Did that make any sense?
Yes.
Or if you still don't get it, well, you have 20 cookies and 2 people. How many people or how many cookies will each person get? How many cookies will each person get? I can't read lip movements.
10 if you're dividing it in half.
10. Exactly right. Okay. Now you have the same number of cookies, but all of a sudden, yes, okay. 5 people showed up at your door. What are you going to do then?
Give each of them 4.
So they will get less number of cookies, right? Okay, so you can say, okay, the number of cookies that each person could get is going to be inversely proportional to the amount of people showing up at the door, right? If you want to distribute equally. Who wants to distribute equally? Okay, guys, I have 700% of grades that I can give. Should I distribute it equally? I got 700%. Should I distribute it equally? Yes,
Yeah.
Dr. O'Brien. Do you think I should distribute it equally?
Yeah, then we'd all get 100.
You all get 100. Then what's the whole point of studying then? But again, yes, okay. But if all of a sudden, yes, okay, your class is being joined by 7 more people. Okay, and I still have 7, yes, okay, 700%. And now if I distribute it equally, yes, okay, what are you guys going to get done?
50.
50. So then the remaining 25% is okay as all your answers on the tests. Okay, guys. So yeah, that may be not okay, but you can see the equation. You can see the relationship, right? Okay. So guys, that's okay. You guys may start realizing slowly and slowly and slowly that okay, yes, it's all about the relationships. Did you guys get that? Okay. Now some of you may then says, okay, so is intensity going to be related to the period? No, it's not. Clear? Okay. Is the relationship going to, yes, okay, sorry. Is power or intensity going to be related to the frequency? No. Is it going to be related to the wavelength? No. Okay, guys? Okay. So tomorrow, yes, okay, we will talk amplitude and try to relate that to, yes, okay, our 2 other bigness parameters. And we will talk propagation speed. Okay. And then we will be done with this chapter here. Then we just have some exercises to do. Okay. And then, yes, okay, this thing is going to start looking more and more and more and more like ultrasound. Now, how was today's class? Oops. A mute answer makes me get worried. Or Hakunat. Okay, guys, now read through these 2, as okay, a couple of topics that we did. And okay, as any questions, either yes, okay, can be asked tomorrow or yes, okay, you can even send me an emails, okay? Okay, guys. Have fun.
See you tomorrow.
Okay, take care, bye. Bye-bye.